Hello everyone, this is Mr. Zimmerman, and today we're going to learn about similar polygons in section 7-2. So first of all, let's take a look at what's in this box here at the top of your notes. And we'll talk a little bit about what it means for two polygons to be similar. So the first thing it says is that corresponding angles are congruent. So if you kind of look at the two figures they have drawn down here, the angles are the same, okay? If the angles are the same, if they're congruent, then it gives the polygons the same shape, all right? But notice that they're not the same size. They're only the same shape. Well, the corresponding side lengths then are proportional, which means that they are going to be in the same ratio. They're going to make the same fraction. And then also there's a little note here. Here's our symbol right there for similarity, okay? So we're going to use that symbol instead of congruent. And so a basic definition of what similar means is it's the same shape because they have the same angles, but the figures are different size. One is a blown up or reduced version of the other one. All right, and the reason they have a different size is because their side lengths are different, but they are proportional, okay? They do make the same fraction. That's about all I'll say about what's in the box, and then the rest of what's in that box at the top of the notes, I'll talk about those concepts as we do the example problems. So let's go ahead and move on to example 1. So the first thing they have in example 1 is they have the similarity statement right here. And it says that triangle RST is similar to triangle XYZ. So then that means that these, they're the same shape, they have the same angles, but they are different sizes. So in part A, they want us to list all the pairs of congruent angles for the figure. Well, we could do this not even looking at the figure because we know the way that we write this statement, we have to match things up in the correct order. So right now we know that the first letter corresponds with the first letter. So that means angle R corresponds with angle X, and since they're similar, those two angles are going to be congruent. The same thing with the second letters S and Y, and then the third letters T and Z. So let's write down all three pairs of congruent angles for part A. So I've listed all three pairs of congruent angles right here for part A. All right, well let's try part B. I'll give you a few seconds to write down part A. So in part B, we need to write down the ratios of the corresponding sides. In part B, we need to know which sides correspond with each other. So if you just look at the similarity statement right here, we know the first two letters, that segment RS, is going to correspond with the first two letters here. That's going to be segment XY. And then the same idea, the second two letters, segment ST, is going to correspond with segment YZ. And then the first and third letter, segment RT, that is going to correspond with segment XZ, the first and third letters. Okay? So then we could do that just looking at the similarity statement. But on this one, I'm going to go ahead and use the figure. We know, looking at the similarity statement, that segment RS is going to correspond with segment XY. But let's go ahead and look at the figures and use the figures for part B. Looking at our similarity statement, again, we know that segment RS corresponds with segment XY. Then this side length of 45 is going to correspond with the side length of 50. All right, then using that same idea, this side length of 27 is going to correspond with this side length of 30. So let's write the ratios of the corresponding sides in part B then. To do this, we need to decide, are we going to do this the side lengths in the little triangle over the side lengths in the big triangle, or are we going to go the other way with the big triangle over the little triangle? So for this one, I'm actually going to look ahead to part C here. And if you look at this right here, it talks about, it's a ratio. It's talking about triangle RST to triangle XYZ. And if you remember in the last video, I talked about the quantity before the word to goes on top, and then the quantity after the word to would go on the bottom of your fraction when you set up your ratios. So let's stick with that. So for this one, that means we're going to do RST on top and triangle the side lengths from triangle XYZ on the bottom. And so really what we're doing then is we're going to do the side lengths of the little triangle divided by the side lengths of the big triangle. I made a little note here that we're going to do the side lengths in the small triangle divided by the side lengths in the big triangle. Then we have a side length of 45 in the little triangle corresponding with a side length of 50 in the big triangle. And then using another pair of corresponding sides, we have a side length of 27 in the little triangle corresponding with a side length of 30 in the big triangle. Well, if you reduce both of these fractions, you could divide the first fraction, the numerator and denominator, both by 5, and you would get 9/10. And then you could do the same thing with the second fraction. You could divide the numerator and denominator by 3, and you would still get 9/10. So what that 9/10 is, that is our scale factor. So if we make a fraction out of any pair of corresponding sides, that fraction right there, that is our scale factor. Now you could reduce it to 9/10. You wouldn't have to, but it'd probably be more convenient if you did. So we've already answered the question then for part C. So we know right now that the answer to part C, the scale factor, is just 9/10. So there's our answer to part C. And here was our ratio of the corresponding sides in part B. Now all we've got to do is part D. Part D says to find the value of A. And we can see that the side length of A in the small triangle corresponds with a side length of 40 in the big triangle. So what we're going to do here is we're going to set up a proportion that allows us to solve for A. Then let's make a fraction. So we're going to have A in the little triangle corresponding with 40 in the big triangle. And then we're going to set that equal to, well, really, we could set that equal to any of these fractions. We could use 45/50, we could use 27/30, or we could use 9/10. It doesn't matter. The numbers will be smaller and it'll be easier to use 9/10, so let's do that. So we're going to set this equal to 9/10. And then we're going to solve this proportion just like we did back in section 7-1. So we're going to do our cross product. So we're going to do A times 10, and we're going to set that equal to 40 times 9. We have 10 times A, well, that's 10A, equal to 40 times 9, that's 360. Then we're just going to divide both sides by the number out in front of the variable, which is 10. Tens are going to cancel on the left side and make a 1, and we get A equals 36. So the length of segment RT, I guess I could write that, RT is equal to 36. Let's turn the page and move on to example 2. In example 2, they want us to determine whether the polygons are similar. And then if they are, then they want us to write a similarity statement, and they want us to find the scale factor. But again, we want to note that the scale factor has to be set up so that it's DEFG to JKLM. Well, again, that means that DEFG, that's going to go on top when we set up our ratios. And then JKLM is going to go on the bottom. So again, we're going to be doing this little quadrilateral over the big quadrilateral. the first thing we want to note is, do these polygons have the same shape? And in order to do that, they have to have the same angles. And so I think you can see we have that. We have angle D is congruent to angle J. Both are marked with 3 arcs. We have angle E is congruent to angle K. We have angle F is congruent to angle L. And we have angle G is a 90-degree angle, and so is angle M. So we have 4 pairs of congruent angles. So we definitely have the same shape. But now we still need, before we can determine whether these polygons are similar, we need to set up the ratios of the corresponding sides. And again, we're going to do this one. We're going to do it again, little polygon over big polygon, or small quadrilateral over large quadrilateral. So I'm going to make a quick note of that. So I made a quick note that we're going to do this one little over big. All right, well, we should see, again, the first 2 letters, segment DE, would correspond to the first 2 letters in quadrilateral JKLM. And we can see that on our diagram also, or on our figure, all right? So DE corresponds with segment JK. All right, well, that means that 15, that side length is going to correspond with the side length of 20. And we can see that the side length of 6 in the little quadrilateral corresponds with the side length of 8 in the large quadrilateral. So that ratio in red is 6 over 8. And we can see the side length of 12, which I did in blue, corresponds to a side length of 16. So I have the ratio 12 over 16. And then the last one will be the ratio formed from the side length of 9, which corresponds to the side length of 12 in the large polygon. So we have to look at these ratios now. They all have to be equal to each other in order for these 2 polygons to be similar. And I think you can see that they are. If we reduce each of these fractions, for example, if we divide the first fraction, the numerator and denominator, by 5, we will get 3/4. The second fraction here, if we divide the numerator and denominator by 2, we will get 3/4, and so on. So if we reduce all these fractions, we're going to get a value of 3/4. So again, that's what we need to occur. We need all of these ratios of corresponding sides to be equal to each other. And if they are, then we conclude that the polygons are similar. And in fact, what we just did there is we just found the scale factor. When we reduced that fraction, again, all we had to do is write a ratio of any 2 corresponding sides. Since they were all equal and we reduced it, that is our scale factor. Let's circle our answer for the scale factor then. And then the only other thing we had to do is we were supposed to write a similarity statement. Well, they were pretty nice to us because we can see the way this original, the way the letters originally match up. They already gave them the letters in the correct order. We already know that angle D corresponds with angle J, so the first letter with the first letter. Angle E has 2 arcs. That corresponds with angle K, which has 2 arcs. And so this is already in the correct order. So all we got to do is write the same thing, but instead of the word 2 in the middle, we're just going to put the similar symbol in between. So let me do that. I've written the similarity statement for you right here. So again, it says polygon DEFG is similar to, using that symbol for similar, polygon JKLM. So that is our similarity statement with the letters in the correct order. Moving on to example 3, they give us that these 2 triangles are similar. They tell us that angle B and angle Q are both 90 degrees, so we should probably mark that on our figure right now. We are also given that the measure of angle A is 30. So let's write that in our figure here so we know this angle right in here is 30 degrees. Well, again, if we know that these 2 triangles are similar, that means all the corresponding angle pairs are congruent. Well, that means we know right now that this angle up here angle P, that's also 30 degrees. All right, and we're supposed to try to find the measure of angle R. That's one of the things that we need, is this angle right down here. So to find angle R, we know that the three angles inside the triangle have to add up to 180 degrees. Well, we know this angle is 90. This top angle up here, angle P, is 30. So then angle R, well, you would just do 180 minus 90 minus 30. That angle R has to be 60. So let's write that down. The measure of angle R is equal to 60 degrees. So we've got that part of our problem done. The other thing we have to do is we have to solve for X, which is the length of segment PQ. Well, all we got to do is set up our proportion using the ratio of corresponding sides. So it doesn't really matter if we do it big triangle over a little triangle or a little over big, and it doesn't matter which pair of corresponding sides we use as long as we know both of them. We know the 9 corresponds to the 6, and we know that 22.5 corresponds to the 15, so we could use either of those. This one, just to change it up, let's do big triangle over little triangle. We're going to use big triangle over little triangle. That's how we're going to set up our ratios. And also, let's use the 9 and the 6. Those correspond to each other. And we have 9 in the big triangle corresponding with 6 in the little triangle. And that has to equal, well, we have X in the big triangle corresponding with 14 in the little triangle. Now we've got our proportion set up, so let's set our two cross products equal and solve. Let me move over here. So we have 6 times X, that's our one cross product. That has to equal our other cross product, which is 9 times 14. 9 times 14 is 126. Then we're just going to divide both sides by the number out in front of the variable X. The 6's will cancel out and make a 1, and we get X equals 21. And there we go. We found the value of X. That was the other thing we had to do. So we found the measure of angle R. We were asked to do that, and we found the value of X. Now again, X would represent the length of the segment PQ. So if we wanted to, we could write the distance from P to Q is equal to 21. All right, let's move on to example 4. I guess before we should do that, we should talk about what's in this box right here. So if we read this, what this says is if we draw any segment inside of our figure, inside of our polygon or our triangle, that same concept will work to solve for any of those segments inside of these polygons. We can use that the corresponding sides, or in this case, the corresponding lengths of these segments are always in the same ratio if the two figures are similar. So let's use that to do the examples, what do we have? We have 4 of them that we have to do in example 4. Problem 1 says we have to find the scale factor of pentagon RSTUV to pentagon LMNOP. So if you look at the figure over here, I think you can see that we're talking about the side lengths for the big pentagon have to go on top, and the side lengths for the small pentagon have to go on the bottom. And again, that's just because the way this is worded. Whatever's before the word 2 goes on the top of the fraction. Whatever's after the word 2 has to go on the bottom of the fraction. So then to do that, all we got to do is match up 2 corresponding sides. That's all we need. We're only given one side in pentagon RSTUV, so we'll have to use that 20 right there. Then we see this side length of 20 in red that I highlighted corresponds with this side length of 16 that I also highlighted in red. So we just got to make a fraction out of that. Again, doing it big over little, and we've got our scale factor. Then our scale factor is 20 over 16. Now, if you want to, you could reduce that. So you could divide the numerator and denominator both by 4, and you would get 5 over 4. So that's our scale factor. Now, if you want to, you could even divide that out into your calculator. You could do 5 divided by 4, and that would give you 1.25, and then you could put that over 1. So you could also use that decimal form of the scale factor, which really means that the large pentagon is 1 1/4 as large as the 1 1/4 times as large as the small one. Part 2 of example 4 says find the length of the diagonal MO. So MO is right here. Well, that's going to correspond with the diagonal SU. So let's set up this proportion and solve for the length of segment MO. Before we do that, let's call that segment length X. And again, we know that corresponds with the diagonal length of 25 in the large pentagon. So let's go ahead and set this up. So since we've already set up our ratios of corresponding sides in part 1, and we did it as big over little, well then let's stick with that on this one. So what we have for part 2 then is the big diagonal would be 25 over the little diagonal that it corresponds to would be X. And then for the other part of our proportion, we could use either 20 over 16 or 5 over 4, or we could use 1.25 over 1. It doesn't matter which one we use. I'm going to go ahead and use the 5 over 4. Then we're going to just do our cross products again. So X times 5 has to equal 25 times 4. So we have X times 5, that gives us 5X. And we set that equal to our other cross product of 25 times 4, which is 100. Then we're just going to divide both sides by 5. And the 5's cancel out here on the left, and we get X equals 100 divided by 5. That would be 20. Since we set this up with X being the length of segment MO, then I guess we could, to wrap this up, since that's what they asked for, is we could write the distance from M to O, or the length of that segment, is 20. All right, we've got 2 more to go. So in part 3 of example 4, they tell us that we have 2 rectangles that are similar, and the similarity ratio is 1 to 16. Well, that's really our scale factor right there, is 1 to 16. Then it says if DE equals 20, what is the length of segment HK? Well, first of all, I think there's a little error on this problem here. If you look at your similarity statement up here, DE is the middle 2 letters. So that should correspond to the middle 2 letters over here for the second rectangle. So those 2 segments would correspond. So I believe that instead of HK, that this should say HJ. So we're going to want to make that change. So I went ahead and made that change. So we're going to find the length of segment HJ instead. And then you don't really have to on this one, but I'm going to draw us a little picture. I just think it helps you visualize what you're doing a little better. So let me draw you a picture. The figure I've drawn is not to scale. But again, the scale factor is 1 to 16, so we know we have a tiny rectangle, and then we have one that's 16 times larger. So let's go ahead and label these things. So it's important when, I don't think I've gone over this with you guys, when you label your figure, so you want to label your rectangle CDEF, all right? So when we label that, we need to wrap around the figure. It doesn't matter what corner or what vertex we start at. It doesn't matter if we go clockwise or counterclockwise. Okay, so I'm just going to do it, here, I'll just do it. So I'm going to do this as CDEF. All right, now when I label the other rectangle, the large one, they are similar, so I have to match the vertices up in corresponding order. All right, so that means that this one, and again, when you do this, you can't cut across diagonally, you must wrap around. All right, even on that first one that I did, you can't go G, H, and then JK. Okay, you can't do that. You must wrap around the figure. So let's go ahead and do that. So this would be G, so G, H, J, and K. We're given that DE equals 20. So this segment length right there, that side is 20. And then we're trying to find the length of segment HJ, so we'll call that X. Again, we can see from our similarity statement that these two letters in the middle have to correspond to these two letters in the middle that I've underlined in red. So segment DE does really correspond with segment HJ. So let's go ahead and make a fraction out of that. We need to be careful when we set up our ratios and our proportion, because our similarity ratio, we were given rectangle CDEF to rectangle GHJK. And that goes with this scale factor they gave us of 1/16. All right, so if you pay attention to how that is again, since CDEF is first before the word to, and rectangle GHJK is second after the word to, that means we have to set this thing up as little rectangle over big rectangle. So I've noted that we're doing this little over big, and again, we have to do it that way because our scale factor was given as little over big. So let's go ahead and write our proportion, and we'll solve for X. Then we have our scale factor of 1/16. Again, that's little over big. And that's going to equal then, we have 20 in the little rectangle corresponding with X in the big rectangle. So we write our second ratio in our proportion as 20 over X. Now let's just do our cross products. So we're going to do 1 times X and set that equal to the cross product of 16 times 20. Our first cross product is 1 times X, which is just X, and then 16 times 20 is 320. So remember, X was our length of segment HJ, that's what we were trying to find. So we can write HJ, the length of segment HJ is 320. All right, on to the last problem finally. The last problem says that triangle HJK has side lengths of 21, 17, and 25. And there's another triangle that is WXY that has two shortest sides of length 39.1 and 48.3. Then it gives you that these two triangles are similar, and they want us to find the length of the third side of the triangle WXY. So let's go ahead. I think you can see that triangle WXY has the longer side lengths for its two shorter side lengths. In triangle HJK, the two shorter side lengths are 17 and 21. So let's draw a picture of this again. I think that'll help you see what's going on. It doesn't have to be perfect. It's just a model to help you do the problem. It doesn't have to be to scale, but let me sketch this for you. Here's my two triangles. My small triangle is HJK, so let's label the vertices HJ and K. And then my large triangle is in the same corresponding order. I'd have angle W, X, and Y at those three vertices. Let's write in our given side lengths. So in the small triangle, I have a short side of 17, and then I have a second longest side of 21, and then I have a longest side of 25. And now when I write these in on the other triangle, I'm going to have to write them in the correct order. So the shortest side in the small triangle would correspond with the shortest side in the large triangle. So I've got to have the 17 side length, the side length of 17 corresponding with the side length of 39.1. So I'll write in my 39.1 right there. And then my second longest side in the small triangle, that would be 21. That would have to correspond with the second longest side in the large triangle of 48.3. So let me write that in. So that would go with the 48.3. So we have to find the missing side in the large triangle. And that's going to be the length of segment WY. I don't want to use X since I already used X as one of my vertices, so maybe this time let's call this L. Now let's set up our proportion with our ratios of corresponding sides. So on this one, I don't know, let's do this one big triangle over little triangle. So I've noted that we're going to do this big triangle over small triangle right here. And then I have two pairs of corresponding sides here. It doesn't matter which ones I use. So if we're going big over small, I don't know, let's use these two. I'm going to use the shortest side in each triangle. Those correspond to each other. So we have 39.1 in the big triangle corresponding with 17 in the small triangle. And that's got to be equal to the side length of L in the big triangle, which corresponds to a side length of 25 in the small triangle. Now let's do our cross products. So we have our first product of 17 times L, so that gives us 17L, is equal to our other cross product, which is 25 times 39.1. That comes out to be 977.5. And then we'll just divide both sides by 17. And we get L equals 57.5. So I'll write 57.5. All right, that's also equal to the third side in the large triangle, which would be the length of the segment WY. So we could write that there also. And there you go. That wraps up the last example for section 7-2. Thanks for watching, and I'll see you soon in class. Bye.